Bond. James Bond.
So today we're going to talk about bonding and the different types of bonds there are. We know the atoms stick together, and there are many different ways there are 3 different ways that they do this. First way is covalent bonding. Covalent bonding is formed by the sharing of electrons. So let's take 2 oxygen atoms, for example. They both have 6 valence electrons. And how they're going to create this covalent bond is they're going to just share these electrons with each other. And then if you count, 1, 2, 3, 4, 5, 6, 7, 8, they're stable. They have 8 electrons. So this oxygen's happy because he's pretending that those are his electrons, and so they're both stable. The next type of bond is ionic bonds. Ionic bonding is formed by the electrostatic attraction between oppositely charged ions. So let's say we have an atom that really wants to give electrons. We have another atom that really wants to take. So who are these atoms that want to give? Let's look at the periodic table. The alkali metals are going to be the ones that want to give. They're unstable. They have very few electrons in their outer electron shell. And the ones that want to take are going to be halogens. So let's do an example here. We'll do sodium, the alkali metal family with 1 valence electron, and then chlorine, 7 in the halogen family. And so for this ionic bond to form, all that's going to happen is sodium is going to give his 1 electron to chlorine. And as he did that, he lost an electron to chlorine, right? So he's now positively charged. And chlorine gained an electron, so he's now negatively charged. And these are the 2 components of an ionic bond. We have the cation, the positively charged atom, and the anion, the negatively charged atom. The last type of bond, and then that forms NaCl, right? So table salt is your end product with that bond. The last type of bond is a metallic bond. So metallic bonds have these outer electrons that are so weakly bound to the metal atoms that they are free to move across the entire metal. So let's use some iron atoms for an example. We have 4 iron atoms. 1, 2, 3, 4. So what happens is when you put all these together, they're going to share all of their electrons in this sort of pool of electrons, this C in between electron. And they're very communal this way. So all of these iron atoms, since they're sharing, they're going to become positively charged. And all the iron atoms will be attracted to this pool, be pulled in by this electron pool that they all contributed to. And this is what allows for metallic properties such as luster and malleability and high melting points and etc. Lewis structures are 2-dimensional representation of a molecule and its valence electrons. So let's the Lewis structure of hydrogen chloride, HCl. So the first step is to find the valence electrons in the molecule. So we have one hydrogen and one chlorine atom. Hydrogen has 1 valence electron, chlorine has 7. You add them together and you have a total of 8 valence electrons. So the next step is to determine the central atom. There's a few rules for this. Either you choose the most electronegative atom, or you know that carbon will always be a central atom and hydrogen will never be a central atom. And also another trick is if there's one element with multiple atoms and one element with only one, usually the element with multiple atoms will be on the outside. So, Cl is going to be in the middle for this one. The central atom. We have 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. And then we have hydrogen next to it with 1. And to create this covalent bond, all that's going to happen is we're going to share these 2 unpaired electrons with each other, creating this bond there. And you have HCl. So the next Lewis structure we're going to draw is Lewis structure for a polyatomic ion. We're going to do sulfate. So with all polyatomic ions, you have this expanded octet that allows for more than 8 valence electrons in the outer shell. But it's the same process. Start with sulfur, which has 6 valence electrons. Oxygen also has 6, but there's 4 oxygens here, so 6 times 4. 24 plus 6 is 30. But we're not done with the total electrons. We still have to look at this charge. This -2 charge adds 2 electrons to the total number. So if you add that 2, you get 32 total valence electrons. So here I've drawn in all of the valence electrons for sulfur and the oxygens. And so we'll start bonding. We have this single bond here and here. A double bond like that. And like that. So if you look, you're checking to see if everything's correct. You notice that these are unpaired. But we have to remember this -2 charge that adds 2 valence electrons. So once we add those in, everything is paired up, and that is correct. So now we can kind of redraw the sulfate Lewis structure. It's going to look something like this. We have sulfate in the middle, the double bond here, the double bond here, single bond. Oxygens. We'll do the valence electrons. And then with polyatomic ions, you go ahead and put them in brackets like that. Whoa, that's a little crooked. And then you write their charge out to the side like that. So, continuing on from this sulfur Lewis structure that we drew, we're going to go over the Vesper theory. And what this is stands for valence shell electron pair repulsion. And it is used to help predict the molecular shape. We assume that valence electrons repel each other. These electrons in these atoms naturally adopt an arrangement in space to minimize repulsion that creates this molecular shape. So these electrons in these atoms are going to try and pull away from each other. They can't completely get away because the nucleus of this central atom is holding them in. But this pulling leads to a molecular shape that has these equal angles because of this force of them pulling on each other. And that is the Vesper theory. And that covers the unit. Thank you for watching.